So we're still in the realm of chapter 6. We're on normal probability distributions. In 6.5, we're going to talk about assessing normality. Now, as a heads up, 6.5 is pretty Excel heavy, so I recommend going through the Excel practices with me either while you're watching this recording or after you've taken notes during this recording. You can go back and work on Excel. So in 6.5, the key concepts in this section, we will present criteria for determining whether the requirement of a normal distribution is satisfied or is it not. These criteria involve 1, visually inspecting a histogram. That means we have to have a histogram to visually inspect. We have practiced making histograms so far in the course. If we make that histogram, see if it's roughly bell-shaped, this is what's meant by visual inspection. We've also done this before, so we can identify outliers. We'll talk more about this. Number 3, we can construct a normal quantile plot. This is where we get very heavy in Excel, so we'll do this today. Let's define this. So what's a normal quantile plot? It's also known as a normal probability plot. It's a graph of points, so x and y, an x-axis and a y-axis, where each x value is from the original set of sample data, and then each y value is the corresponding z-score that's expected from the standard normal distribution. We will practice making these today. Let's talk more about those 3 requirements. So here's the procedure for determining whether it is a reasonable assumption that sample data are from a population having a normal distribution. In other words, we have a population, we have a sample from that population. Is it safe to assume that those sample data are from a population that has a normal distribution? So number 1 again is making a histogram. We have to do that first if we don't have a picture of a histogram in front of us. If the histogram departs dramatically from a bell shape, we can conclude that the data do not have a normal distribution. We'll look at an example of this. Number 2, we're going to identify outliers. If there is more than 1 outlier present, conclude that the data might not have a normal distribution. If you'd like more of a refresher on outliers, we first saw these in Chapter 3, Section 3. We're not going to talk about outliers again in 6.5. Rather, we're going to talk more about these normal quantile plots. So sort of step number 3, if we've gone through these and we're still unsure, then we can use Excel and we can make a normal quantile plot. The book talks about using Excel's XL stat add-in. We're actually not going to do that. The Excel XL stat add-in would make a normal QQ plot. Today, we're going to make a normal quantile plot, which is slightly different than a normal QQ plot. However, if you would like to know more about these normal QQ plots, let me know separately, email me, message me, and we can talk more about that. If you're thinking these normal quantile plots sound familiar, it's because we have seen these before. So we first saw these in Chapter 2, Section 2. This was when we were first looking at types of graphs. So if you want to go back and look at that for a refresher, you're welcome to do that as well. Now again, the focus is going to be more on these normal quantile plots and not as much on histograms and outliers again. So within number 3, these normal quantile plots, we're going to apply the following criteria to determine whether the distribution is normal. Now, this is an important note. So these criteria can be used loosely for small samples, but they should be used more strictly for larger samples. This is because the larger of a sample we have, the more likely it is to represent the true population. So if we have a ton of numbers in our sample and those still don't resemble a normal distribution, then we're probably not dealing with a normal distribution. If we only have a few small number of samples, then again, this is why these criteria can be used a little bit more loosely. So when we have a normal distribution, the population is normal if the pattern of the points is reasonably close to a straight line and the points do not show some symmetric pattern that's not a straight line pattern. Again, we did see this previously, so you can go back and look at other examples of these normal quantile plots. If we make a normal quantile plot and we end up concluding that it's not a normal distribution, then the population is not normal if either or both of these two conditions apply. The first, the points do not lie reasonably close to a straight line, and or second, the point shows some symmetric pattern that's not a straight line pattern. Let's look at some examples of normal distributions and not normal distributions. We'll look at both a histogram example and a normal quantile plot example. So on the left here, we have a histogram of IQ scores that's close to being a normal bell-shaped curve. This suggests that this is a normal distribution of the data. Then on the right here, we have an example of a corresponding normal quantile plot from this same set of data. These data are reasonably close to a straight line pattern, and the points do not show any other systematic pattern other than a straight line. So from either this example, so this histogram, or looking at the normal quantile plot, we can conclude that these IQ scores are from a population that has a normal distribution. Next, let's look at a uniform example. So again, here's our histogram. We have a uniform or very flat distribution of all of these data. The normal quantile plot that corresponds to this uniform example looks like this. So what can we observe from this normal quantile plot? Well, we can see that these data points are actually reasonably close to a straight line. However, very importantly, there's another sort of systematic pattern that's not a straight line pattern. What is that other pattern? Well, it kind of looks like this sigmoidal curve here. So because we have this other pattern here, we can see from the normal quantile plot, then either from this histogram representation or this normal quantile plot representation, we can assume that these sample values are from a population having a distribution that is not normal. Again, even though these do resemble somewhat of a straight line, we have this other nice looking pattern here that resembles a curve to it. So because that other pattern is there, we can't say that this sample data here comes from a population that has a normal distribution. Let's look at a third case here. So a skewed example. Here's our histogram. This histogram is certainly not bell-shaped. It's definitely skewed to the right. The corresponding normal quantile plot for this histogram looks like this. We can tell right off the bat that these data do not resemble a straight line. So from either one of these representations of this sample data that's from a greater population, we can conclude that these rainfall amounts are from a population having a distribution that is not normal. Okay, so we've looked at examples of this. We can determine if these are a normal distribution or not a normal distribution. Well, what if we don't have these images right in front of us and we need to create either a histogram or a normal quantile plot? Well, here are some tools for determining normality. The first is creating a histogram and looking for outliers. If we make a histogram, it's roughly bell-shaped and the number of outliers is 0 or 1. We should treat that population as if it has a normal distribution. If you would like a refresher on making histograms and identifying outliers, definitely check back to 3.3. Another tool are these normal quantile plots. Again, we're going to practice making these twice today. The third tool are considered these advanced methods. There's some statisticians that came up with a way to assess normality. There's pros and cons to these different methods. These won't be discussed any further in 6.5, but again, if you are interested in these, let me know, we can talk more about them. So we've been building up to this. How do we construct these normal quantile plots? We're gonna go through step by step in Excel. Okay, so keep in mind, this is a manual construction of a normal quantile plot. Let's go through this step by step. Step number 1, first sort the data by arranging the values in order from lowest to highest. You've been instructed to do this as part of one of your Excel assignments. So to do this, we first want to take our set of numbers. In this case, I'm using an example with just 1, 2, 3, 4, and 5 as our data points. In the next example of making another normal quantile plot, I'll show you again how to sort this data from least to greatest. Here for this example, we only have 5 data points, so 1, 2, 3, 4, 5, so we can rank these by hand. Okay, so that's step number 1. Step number 2, with a sample size of n, each value represents a portion of the sample. So this is saying that we need to know what our sample size is. In this case, we have 1, 2, 3, 4, 5 samples. So we have 5 total number of samples here. So lowercase n, we have 5 samples. Now that we know our sample size, so sample size n is equal to 5, we're going to find the values of 1 over 2n, 3 over 2n, 5 over 2n, and so on, if you see the pattern happening here. So the next one would be 7 over 2n. The next one would be 9 over 2n. Right, so we have all these odd numbers here in the numerator. And the denominator doesn't change. It's always 2n, 2n, and 2n, and so on. We need to establish this up until we get n number of values. So in our case, we would need to do this 1, 2, 3, 4, 5 times because we have 5 number of values. Because we have 5 number of values, 5 goes in here to replace lowercase n in this formula. When we calculate these values are the cumulative areas to the left of the corresponding sample values. So in Excel, what will that look like? Well, we have our set of numbers, 1, 2, 3, 4, 5. We have 5 data points in our sample. Step number 2, for 5 total samples, we need to do this formula 5 different times. What that's going to look like for this case is I'm taking 1 over 2n, where that becomes 1 over 2 times 5. Okay, so that's shown here, 1 over 2 times 5. The next row down, I'm doing the next step in this, so 3 over 2 times 5. The next step, 5 over 2 times 5, 7 over 2 times 5, and 9 over 2 times 5. We only have 5 data points here, so I'm doing this 1, 2, 3, 4, 5 times. In this column, I've showed you how I set up the calculation, and in this column is where I have my answers. So it's basically this equation. I hit enter, I got 0.1, 0.3, 0.5, 0.7, and 0.9. Why did I do this only 5 times? It's because I have 5 total data points in this sample. Let's go to step 3. So we're going to use standard normal distribution software, a calculator, Excel, or table A2. Today we're going to use Excel. We're going to use Excel to find the z-scores corresponding to the cumulative left areas found in step 2. What that's going to give us is the z-scores that are expected from a normally distributed sample. Let me show you how to do this in Excel. Keep in mind this is a new function in Excel you haven't seen before. And I do encourage you to use Excel here rather than table A2. So let's see what this new function is. This new function is NORMSINV. It's basically standardized normal distribution. It's another inverse function. Let me show you how to use it. So here on the left, we have our sample data. Here in step 2, we took 1 over 2 times n, 3 over 2 times n, and so on. We got these values here from step 2. Now in step 3, I'm going to use this new function, so equal sign to set up the function, NORMSINV. I want to take this function of this value here from step 2. So we take the norms inverse of 0.1. We take the norms inverse of 0.3, norms inverse of 0.5, norms inverse of 0.7, norms inverse of 0.9. Again, I'm doing this 5 times because I have 5 data points in my sample. In this column, I'm showing you the setup. In this column, I'm showing you what you should get when you click enter, so the values you should get here. One thing you can check for yourselves is that these should be the minus version and the plus version of the same number. Same with these values here, and then you should get 0 in the middle for the middle data point in your sample, after you've ranked the samples from least to greatest. Hopefully you're following along with me either in Excel now or you're going to use Excel later. To make normal quantile plots, the best way really is to use Excel and to follow these steps. So that was step 3. Let's keep going. Step 4, match the original sorted data values with their corresponding z-scores found in step 3. Then plot the points, so x, y, where each x value is an original sample value, so that 1, 2, 3, 4, 5, and each y is the corresponding z-score we found from those norms inverse functions. Now, the best way to plot this is to really copy and paste this data into a new set of columns somewhere in your Excel sheet. So now I've moved over a couple columns. I have my same set of numbers from the beginning, so 1, 2, 3, 4, 5. In the next column over, I have my z-scores that I calculated in step 3. Excel really works best when making plots when you have your x data right next to your y data. Now, once we have our data organized like this, we have our x values and we have our y values, we're going to select the data of interest that we want to make a plot for. So in this case, I would highlight these boxes here by clicking and dragging. You should include these headers here, so the set of numbers and the z-scores. So I'd select this point to this point and drag and highlight that data. Once I have that data highlighted, I'm going to add a chart. So we have our data highlighted. We go to Insert, XY Scatter. So again, we have our data highlighted. I go to my Insert tab. I find these chart diagrams. I hover over this one. This is my scatter plot option. Then I go to the first one where I have a scatter plot with no lines. Once I've clicked on this, I'll get a graph that looks like this. Now you won't have a line here yet. I'll show you how to add that line on the next slide. One thing that also won't populate automatically are these axes labels. You should feel comfortable adding these axes labels based on our Excel assignment so far. If you don't feel comfortable with that yet, let me know ASAP and I'll show you how to add those. So I have my y-axis, I have my x-axis, then I also changed my chart title to be y-axis versus x-axis. My y-axis are my z-scores, my x-axis are my data values in my sample. Now, part of assessing normality is if these data points resemble a straight line. So you could visualize this without adding the straight line. I also will show you how to add that straight line in Excel. So this brings us to step number 5, examine the normal quantile plot and use the criteria given earlier. Conclude that the population has a normal distribution if the pattern of points is reasonably close to a straight line, and the points do not show some systematic pattern that's not a straight line. So to add a straight line, we're going to want to be clicked on the graph of interest. We go to the Chart Design tab, then go to Add Chart Element, then add Linear Trend Line. Okay, so under Chart Design tab, go to Add Chart Element, go down to Trend Line, click on Linear. That will create a line here that creates a trend line for your data. So we're at the end of this example. We only had 5 data points, but we made a normal quantile plot following all of those steps. Based on this linear trend, we could say that this is a sample of data from a population that has a normal distribution. Why? Because we made this normal quantile plot, and this line is linear, and it also doesn't have any other systematic pattern to it. Now, not all data sets will have 5 data points to look at. Let's do a more complicated example now. Let's do this with the Old Faithful eruption times. Within this set of data, there are 250 eruption times. So now we're going to apply everything we did with 5 data points to now 250 data points. So follow along with me. This is data set number 23. You can follow the instructions in the Excel assignment number 2 instructions to access this data and practice. You should do this. I promise you, your future self will thank you. So again, the previous steps apply, but this is with a large data set. So in the rest of this lecture, I'm going to show you some tips and tricks for how to apply Excel formulas to a larger data set other than just 5 points. So once we have data set number 23 copied and pasted into our Excel sheet, we're going to want to only work with the second column of data. That second column of data is the duration data in seconds. Now, when you originally get all the data set for Old Faithful eruption times, there's a lot of data there. So we're going to copy and paste that column specifically into a separate part of the document. Then step number 1 is to sort that data. To sort that data, this is under the Data tab, go to that A to Z icon. This is what it looks like. We go to that Data tab, we click on that A to Z icon. First, though, you need to have your data highlighted that you want Excel to sort for you. In this case, you don't want to highlight the duration heading, you just want to highlight the numbers underneath. So click and drag to highlight all those numbers, go to your Data tab, then sort the data from smallest to largest. Okay, so now we got that step down. Next, we're going to go to the next column over, type in rank. The headings here aren't that important, but this is how I'm going to set it up. In that column titled rank, we're going to type in at least 1, 2, and 3 into the rows below that heading. Then this is one of the tricks for applying a certain formula to a large set of data. So we're going to highlight those cells 1, 2, 3, then double click on this small green box in the bottom right of the cell with 3 in it. What that's going to look like now is we have our duration time in seconds, and the next column over I've typed in rank. Then I've typed in 1, 2, and 3. Then I've highlighted the cells that 1, 2, and 3 are in. That small green box I was talking about in the bottom right of the cell with 3 in it is right here. You're going to want to double click on that green box. It will transfer the pattern down to all of the appropriate rows in that column. This is what it looks like. So now we have 1, 2, 3, 4, 5, 6, all the way down for each data point in your data set. That small green box pattern is a really, really handy way to not have to do this manually. You wouldn't want to have to manually type in 1, 2, 3, 4, 5, 6, all the way through 250. So this is how you do it. Then scroll all the way down to the bottom of your data set. We were told at the beginning that there are 250 samples, but we can also go down to the very bottom of our data set and verify that for ourselves. So with the largest time here, right, because it was ranked smallest to largest, this corresponds to the 250th data point. That means there are 250 data points in this sample. Okay, then in the next column over from that, type in rank proportion. Again, these headings don't really matter, but this is how I'm going to set it up. In the first row under this heading, type in an equal sign because we're going to start setting up a function. Okay, so far we have rank proportion typed in here. We also have an equal sign typed in. Next, type in an open parentheses, then click on this first cell corresponding to rank number 1. It's really important that you don't type in 1, but instead you click on the cell with the number 1 in it. So far we have equal sign, open parentheses, and then the cell identifying where rank number 1 is. From that, I want to subtract 0.5, so type in a minus sign, then 0.5, then close parentheses. In the previous slide, we found out there are 250 samples. We confirmed that. We want to take this value here and divide it by 250, the total number of samples that we have. Okay, so the setup should look something like this. You might not have your rank values in column I, that's okay. As long as this identifier here, so column I and row 3, refers to your rank number 1, then you're all set. If you're wondering why we're using this version of the fraction instead of the one we used earlier with the 1 over 2 times n and 3 over 2 times n, this is the same thing. It's a little bit simpler of a way to represent it. So again, we should have a setup that looks like this. Then I click enter and I get my first value, which corresponds to rank number 1 and then the first rank proportion. After I've clicked enter for this, I've gotten my answer. I'm going to find that small green box again in the bottom right corner and double click it. Okay, so double click that green box again so the pattern transfers down to all of the appropriate rows that we want it to. What you should see when you do this is something like this. Excel will automatically take this second rank and apply the same formula. If you click on this one, you would see I4, in my case, minus 0.5, still divided by 250. In the next row down, it's going to take I5, which corresponds to rank number 3, minus 0.5 divided by 250. It's going to do that for every single rank value that you put in. So it'll do that for rank 1 through 250. Scroll down and just check that for yourself and see that Excel did that for you. Then, in the next column over, label that column as rank-based z-scores, or just z-scores, something that makes sense to you to stay organized. We're going to use that new function again we learned today, so norms inverse function. Instead of typing all this in manually like we did for the first example, we're going to have Excel help us out. So here's what this looks like. We have our rank-based z-scores column here. Then we're going to take the norms inverse function of all of these rank proportion values. Instead of manually typing in equals sign norms inverse of 0.002, then in the next row, equals sign norms inverse of 0.006. That would take a lot of time. So instead, we're going to take that double clicking the green box strategy again. In order for that to work, we need to type in equals sign norms inverse function. Then instead of typing in 0.002, you want this to reference the cell where this value of 0.002 is. Then close parentheses. If you don't type that in, Excel will do that for you. So once you have this set up, click enter, you'll get your first rank-based z-score corresponding to a rank proportion of 0.002. This rank proportion corresponds to rank number 1, which then also corresponds to our duration value of 95 because we sorted all of these values here that were in the duration column. Now again, we're going to double click that green box so the pattern transfers down to the remainder of the column. So you've had this typed in, you click enter, it gives you this answer. Then you find that small green box, double click it, it will transfer that pattern all the way down to 250 data points. What that's going to look like is something like this. When you scroll all the way down to the bottom, here's our largest data point, our rank of 250, the corresponding rank proportion, then the rank-based z-score here that Excel did for you. Next, we're going to make a plot. Now, it's a little bit trickier because we have 250 data points. So let's talk through this. To make a plot, it is easiest if we copy and paste over the original data of interest, so that duration column. The original data of interest is our X values. So Excel really works best if we have our X data right next to our Y data. So we want these duration values as the X data, then the Y data are those rank-based z-scores that we just set up to calculate in Excel. To copy and paste, you want to select all the data that you want to copy and paste. Depending on if you have a Mac or a PC, you'll type Control-C to copy and Control-V to paste, or some slight variation if you have a Mac or a PC. But don't go too fast with this because there's one other really important point here. We need to be extremely careful when we're doing this with the rank-based z-scores because there's formulas embedded within those cells. So to do this, we would highlight our rank-based z-scores by clicking and dragging, then click copy. Then when we're going to click paste, we need to do something special here. So here's my duration in seconds. It's already copied and pasted into this column. Then I've selected all of my rank-based z-scores, including the heading here. I've hit Control-C to copy. I'm ready to paste those into column N. But to do this, I'm going to paste them right here. So I've clicked on that first cell. Rather than just clicking paste right away, we need to do a slight variation on paste. So I'm clicked on this cell, I have this data copied. I'm going to right click, go to paste special, then instead of just straight pasting everything that's in here, that has functions that would refer to other cells. Instead, I'm going to click paste special and just paste the values themselves. Okay, so when I've selected the rank-based z-scores, I've copied, then I've clicked where I want them to be pasted. Instead of just straight pasting them, I'm going to right-click, paste special, and just paste their values, or values only. Okay, now we're almost there. So we have our X data, so the duration in seconds, right next to our Y data, our rank-based z-scores. It should look something like this. We have our duration in seconds, all of our data still sorted, our rank-based z-scores, just the values now, they won't contain a formula. Then I want to make a scatter plot. So I would highlight all this data again, insert an XY scatter plot, also add a trend line to help us better visualize what we're seeing, so then we can better assess normality. So here's what it should look like when I have all of my data dragged and selected. I inserted an XY scatter plot, then I added that trend line here. Based on this normal quantile plot that we just beautifully crafted, we can see that this is not on a linear pattern. These data points are more of a sigmoidal curve again. The main takeaway is that they're not a linear pattern, right? In 2 slides from now, we'll talk more about this conclusion. First, I want to come back to this. So in your textbook, if you're reading along in 6.5, you'll see this sort of plot to this QQ plot. If you would like to talk more about this, definitely let me know. In the meantime, go ahead and get really comfortable with making these normal quantile plots that we've done now twice with the 2 examples. Coming back to the plot we made, let's actually assess it for normality. We could have definitely made a histogram in Excel. You've done that in one of your Excel assignments. It's also described in 2.2. If you made a histogram instead of a normal quantile plot, you would see the histogram is skewed to the left. It's also far from bell-shaped. If you wanted to then look for outliers, an examination of the sorted list of those 250 eruption times would reveal that the lowest 20 times do appear to be outliers. Again, this would take additional work to make a histogram and also see if there are outliers on that histogram. What we do already have for this data is this beautifully crafted normal quantile plot. We can see that our data points here are very far from a straight line pattern, right? They have a very significant curve to them. So from this normal quantile plot, we conclude that the 250 eruption times do not appear to be from a population with a normal distribution. One last bit to talk about, so these different data transformations. We've talked a lot about normal distributions, but most data sets have a distribution that's not normal. But we can transform the data so that the modified values have a normal distribution. One way of doing this that we haven't really talked about is using logarithms. You can use a natural logarithm or logarithms with base 10. We're not going to talk more about this in 6.5, it's just something to be aware of in the realm of statistics. Using logarithms, if the distribution of the logarithms of the values is a normal distribution itself, then the distribution of the original values is considered a log normal distribution. Again, that's if we have a set of data, we take the logarithm of that set of data, each data point, then we plot the resulting logarithmic data. If that itself is a normal distribution, we call that a log normal distribution. I showed you an example here, but again, we won't really touch more on this in 6.5. We are at the end of 6.5 now, so that was assessing normality. Really practice using Excel. You'll also get more practice with your MyStatLab homework. Let me know if you have any questions at all. I'll see you next time for the last section of Chapter 6, so on 6.6. I hope you're all doing well, and I'll talk to you soon.